Hi guys, so this is just going to be a short video just to help you with exercises 11E and 11F. And we're going to focus on two things. One, finding the angle between two vectors, and the other is just modelling with vectors as well. So we talked at the very beginning of this chapter about what a vector is. So some examples of the vectors that we could use are displacement, velocity and force. And then examples of scalar quantities are length, speed and mass. And what you might think to yourself is that, for example, some of these are related. So, for example, displacement is related to distance, but it's from a certain point. So that could be positive or negative from a certain point. We also know that velocity and speed are linked as well. So velocity will tell us not just our speed, but from a certain point. So it could be positive or it could be negative. And remember as well that velocity could be our vertical velocity, and we could have a horizontal velocity there as well, whereas speed will just be in one dimension. And then there is also a connection between force and mass, but you'll cover that a little bit more in mechanics. So one thing that we'll need to recap is just how to find the magnitude of a vector. So we did this in a previous team session, I believe. So for example, if I want to figure out the magnitude of the vector here, AB, so if to get from A to B, I go 3 right and 4 up, then to find the length of this line, we said that we just use Pythagoras' theorem. So we literally just say it's the square root of 3 squared plus 4 squared, which is just going to give us 5. Okay, remember you can just type that into your calculator. If I wanted this vector here, it will be the square root of 1 squared plus minus 1 squared. So that's just going to be the square root of 1 plus 1, which is just going to be root 2 there. Okay, remember that if you square a negative number, it's just going to become positive. And you guys get the idea, so therefore, if I did this one here, then that's going to be the square root of minus 5 squared plus minus 12 squared. And if you type that into your calculator, that's just going to give you 13 there. Okay, on to the next ones. There doesn't have to be a drawing there. All that this is going to be is the square root of 4 squared plus minus 1 squared. So that's just going to be the square root of 17, just like that. And you could do the same here. If we know, for example, you could still use the formula on this last one here, but if one of the components, either the horizontal or the vertical, as it is in this case, is 0, well, it's just going to be too long, okay? So I don't really need to do that. It will just be 2 there, okay. Okay, so now we're going to look at how we might involve angles or perhaps areas of triangles here as well. So on this question here, it says we want to figure out, let's say we want to figure out the area of triangle ABC here. So just to start off with, it says that the vector from A to B is 3i minus 2j, so that's just this vector here. The vector from A to C is I minus 5j, so that's there. And it just wants us to find the angle BAC. So if I trace it out BAC, it's this angle here that I need to find. So this is linked to trigonometry that you learned earlier in the year. Obviously, this is not a right-angled triangle, but first of all, if I look at the sides of the triangle, rather than have vectors, I'd rather just have lengths there. So what I could do is for each side, I could figure out what the magnitude of the side is. So for A to B, I'll just figure out the magnitude of that. So that's just going to be the square root of 3 squared plus minus 2 squared. So that's just going to be root 13 there. I'm just going to keep it as a surd as well, because perhaps later on I might square that afterwards and then I won't be left with any decimals there. Okay, I could do the same for AC here. So this is just going to be the square root of 1 squared plus minus 5 squared. That's just going to be root 26. And then last of all, if I wanted to, I could figure out the vector from C to B. So I'm not given that straight away, but what you can see is that I can go from C to B by going up to A and then down to B here. So basically that's going to be C to A plus A to B. So C to A plus A to B. Now, I don't have C to A straight away. I've already got A to C, so I could just use minus A to C if I wanted to instead. So that's the same as minus A to C plus A to B. So therefore, I could just write that as A to B minus A to C. I could have derived it like I've done there. I could have just remembered that to get that vector, all I've got to do is take away A to C from A to B. That's all I could do there. So A to B is 3 minus 2. A to C is 1 minus 5. So that's just going to be 3 minus 1, which is 2, and minus 2 minus negative 5. So that's going to become a plus 5. So minus 2 plus 5, and that's going to leave me at 3 there. So now that I have that, I could write that here. Then I could figure out the magnitude of that vector. So that's going to be the square root of 2 squared plus 3 squared. So the square root of 4 plus 9, which is also going to be root 13 as well. So now if I want to figure out the angle BAC, so this angle just here, I've got all of the sides, but I would like an angle. It's not a right-angled triangle. So what I'm going to use is either the sine rule or the cosine rule. So I've only got one angle involved, so therefore I'm going to use the cosine rule. So strictly speaking, I could have used right-angled trig here because you may have noticed that this is an isosceles triangle. So there is a way of doing it with right-angled trig, but we'll just do it generally if it were any triangle. Okay, so let's just write down what the cosine rule is. So we've got a squared equals b squared plus c squared minus 2bc cos A. So just remember to yourself that when you're labelling these, the capital letters are angles and the lowercase letters are sides here. So we're looking for A here. So therefore, we've already got what the length A is. That's the side opposite the angle A. And then B and C, I could just use either there, whichever one I wanted to use. So you might have remembered as well that you might have just remembered straight away what the rearrangement of this is. So I could say that the cosine of A is equal to A squared minus B squared minus C squared all over minus 2BC, which you probably just write down as this. Cos A is equal to B squared plus C squared minus A squared all over 2BC, which of course, once you've got that, then you can just use arc cos or cos minus 1 to figure out what your angle A is there. So let's write down what we've got then. So we're saying that A is opposite here. So A is going to be, and remember we're using the lengths, not the vectors here. So A is going to be root 13. Let's say that this side here could be B. So A to B could be B. So that will be root 13 too. And then C is root 26. So what I'm going to do now then is just to put all of that into this formula here. So I've got root 13 squared plus root 26 squared. I'm aware that you'll probably do this in your head at the top here. Minus root 13 squared. All over 2 times root 13 times by root 26. And that's going to give me the cosine of the angle A. So you could literally type that into your calculator, or you could work it out bit by bit. So what we'll be left with then is the cosine of A is equal to, and it gives me root 2 over 2. Therefore, A is going to be equal to arcsine of root 2 over 2. And that's just going to give me 45 degrees. So A equals 45 degrees. If you know your exact values, then you don't strictly need to use a calculator there. So I've got that the value of A there is 45 degrees. Right then. So if I simplify this diagram here, and I'll just continue it on the next slide in a moment, I'll just be left with a triangle here like this. This angle here is 45 degrees. This side is root 13. This side is root 26. And this side is root 13 as well. So let's say that I wanted the area of this triangle. So as you can see, it's not a right angled triangle, so I'm not going to do half base times height. It's a triangle with 45 degree angle in. So I can just use half AB, so the area is equal to half AB sine C. So therefore, that's just going to be half Remember, A and B are the two sides enclosing the angle there, so it's going to be root 13 times by root 26 times by sine 45. So therefore the area is going to be 13 over 2 or 6.5, and then that would be it. Okay, so now you should be able to do, from what we did in the team session on Thursday and this video, you should be able to do exercise 11E in the textbook now. Moving on to modelling then, so if we have a look at this, it says, in mechanics you will see certain things that can be represented as a single number without direction or as a vector with direction. So, for example, we might have here, and we talked about this earlier, a vector quantity might be a velocity. So that might mean that because it's given in kilometres per hour here, it means that it will go 3 to the right, well, because it's kilometres here, every hour it will go 3 kilometres to the right and 4 kilometres up. But the equivalent scalar quantity might mean here that we just want the speed instead. So, and this is normally what we'd probably use in real life, would be just to say the speed. So we wouldn't say I'm moving 3 kilometres to the right and 4 kilometres up. We'd just say what the actual distance is that we're moving in an hour. So if 1 hour I go 3 to the right and 4 up, I just want to find the hypotenuse here. So therefore, all I've got to do is to find the magnitude of that vector. So if you've got the velocity vector and you want the speed, then all you've got to do is find the magnitude of that vector. So that, for example, that's just going to be the square root of 3 squared plus 4 squared, which is just going to be 5 kilometres per hour. So if you just look across this line, that will be 5 kilometres per hour, which is just equivalent to going 3 kilometres to the right and 4 kilometres up in an hour. Displacement, well, the equivalent scalar quantity here is going to be distance. So distance is like speed. It's not going to be positive or negative. It's just going to be how far away something is. Whereas displacement could be negative because you're moving from a fixed point. And this is going to be similar. So all we've got to do is to figure out, well, if I've gone, and I could write this if I wanted to. So if I have a point here, I've gone 5, in fact, let's do it here, 5 to the left and 12 up. That's the displacement. So rather than saying that I've gone 5 kilometres to the left and 12 kilometres up, if you want the distance, you just say what the magnitude of that line is there. So therefore, it's just going to be the square root of minus 5 squared plus 12 squared, which is just going to give you 13 kilometres. Another example with modelling then might be when we're using bearings instead. So it might be that you use bearings and you've got a right angle triangle, or sometimes you might use bearings and you don't have a right angle triangle. So trigonometry is probably going to be involved here because we're looking at angles as well as distances. So if we read this question, then it says a girl walks 2 kilometres due east from a fixed point O to A, and then 3 kilometres due south from A to B. Find the total distance travelled. So this is fairly straightforward. So because it's distance, I've travelled, or she's travelled, 2 kilometres here, and then another 3 kilometres here. So in total, she's just travelled 5 kilometres. Okay, so it says then the position vector of B relative to O. So for this then, we want the position vector here of B from O. So pretty much just how do I get from O to B? So I've just got to go 2 to the right, and then 3 down. So I could write it like this, or I would probably write it like this, 2i minus 3j. The next part just wants the magnitude of that vector, so the magnitude of O to B. So in other words, the magnitude of 2 minus 3, which is going to be the square root of 2 squared plus minus 3 squared. So that's just going to be square root of 4, add 9, so root 13 there. Okay, so part D is slightly more difficult because it wants the bearing of B from O. So what you need to remember is that if we're doing bearings, a bearing is always measured from north, and it always has 3 figures, okay? So if we're going to B from O, north is up here, And then we want to know how far we have to turn to be facing B there. So we want all of that angle there. Well, the first part is fairly straightforward. We know that this here is 90 degrees because A is due east. So just remember your compass points, north, east, south, west. Each one of these is just 90 degrees turn to get to the next one. So that's just 90 degrees. So we need to figure out what this angle theta is here. So we could do this in quite a few different ways. So it's completely up to you how you do it. You could use the hypotenuse now that we had root 13. We just want this angle. This, remember, is a right angle as well because then she travelled south. So east and south are at a right angle too. So therefore, we could use the 2 and the 3 or the 3 and the root 13. I'm just going to use the 2 and the 3 because they're given to me in the question. So if I do that, then here is my angle. So this side is adjacent to the angle and this side is opposite. But it's perfectly fine if you wanted to use the hypotenuse and use one of the other trig ratios. So if it's adjacent and opposite, it's just going to be tangent. So the tangent of that angle is going to be equal to the opposite over the adjacent. So 3 over 2. Therefore, I'm just going to say that theta is equal to arctan 3 over 2, which is going to be 56.31 degrees, and that's just to 2 decimal places. Just remember though that the actual question wanted the bearing of O from D, so we wanted all of this angle here. So then the bearing for the last part, I'll have to add on that 90 as well. So 90 plus 56.31 is going to be 146.31 degrees as a bearing. It's already got at least 3 figures, so that's absolutely fine. Okay then, so on this one it says we have, in an orienteering exercise, a cadet leaves the starting point O and walks 15 kilometres on a bearing of 120 degrees to reach A, the first checkpoint. From A, he walks 9 kilometres on a bearing of 240 degrees to the second checkpoint at B. From B, he returns directly to O. And then we've got to do quite a lot of questions there. So what I think would be really helpful here is that we need to draw a diagram. Okay, so like it says over here, first of all, draw a big diagram just so you can see what's happening. Okay, so first of all, a cadet leaves the starting point O. So I just need to write down my starting point here is going to be O. And then he leaves on a bearing of 120 degrees to reach A. So 120 degrees is going to be somewhere just like that. Okay, I'm not going to draw it accurately, but that's going to be A there. And it tells me that he walked 15 kilometers and that was a bearing of 120 degrees. Then from A, he walks 9 kilometers on a bearing of 240 degrees. So remember, we're going from north again. 240 degrees, so remember, all the way around here to there will be 180, so a little bit further, 240 degrees and 9 kilometers in that direction. And that will lead us to point B. And then from B, he returns directly to O. So it's just going to go back up here to O there. So this wants, first of all, the position vector of A relative to O. So at the moment, I can't figure that out straight away because if I want the position vector, this is very similar to what you were doing a few lessons ago when you had the angle and magnitude form of writing a vector, or magnitude direction form of writing a vector. So here what you can notice is you could use right angle trig. And then if you had a look there, that's now a right angle. And if I want to know O to A, so the position vector of A relative to O, that's just O to A. So I need to know how far across, how many I, and then how many down, which would be J there. So we know that that's going to be 90 degrees there. So therefore, this part of the triangle there is going to be 30 degrees. So I've got the hypotenuse and I've got 30 degrees. And you might remember this from what we were doing before. So if, let's say, first of all, I want to figure out, that can be the hypotenuse, this would be the adjacent, this would be the opposite. So if I want to figure out how far, or the I component here, I need to figure out the adjacent side. So adjacent and hypotenuse is going to be cosine. So I know that cos of 30 is going to be adjacent over our hypotenuse. So adjacent over 15. So my adjacent component is just going to be 15 cos 30, which is going to be 15 root 3 over 2. Or I could round that and it's going to give me 13.0 to 1 decimal place there. If I wanted the j component, I need the opposite side here. So then that's going to be using sine because I've got the hypotenuse there. So it's just going to be sine of 30 is going to be equal to opposite over hypotenuse. So the opposite is equal to 15 sine 30. So therefore, the opposite side is going to be 7.5. Okay, and remember, both of those are in kilometres, but now we've got our I notation and our j notation. I could write it as, our I component, sorry, is 13, and our j component there is 7.5. So that would be O to A there. One thing actually that we might notice here is that actually, because it's going down here, this should actually be minus 7.5 there. Okay then, so for part B, we wanted the magnitude of O to B. So we can't do that immediately. But what you might see is that if I just want the magnitude of O to B. I don't need to figure out what O to B, the vector, actually is. I just need to know what the length of this line here is. So if you think I've got two lengths in this triangle, and then if I wanted to, I could also figure out from this little red triangle that I drew, this is 30, this is 90. So therefore, this is going to be 60 because of angles in a triangle. And then I could figure out what this would be here as well. So 240 plus 60 is 300. All of these are around a point, so that's going to be 60 degrees as well there. So 360 minus 300 just leaves me with 60 there. So I've now got two lengths and an angle inside the triangle. I want the other angle, so if the other length, so if 3 lengths are involved, I'm going to use the cosine rule. So that's going to be a squared is equal to b squared plus c squared minus 2bc cos a. So it makes sense for me here because I want a squared, so I'll just call this side a here. So whatever that is, ob squared is equal to b squared. So let's say that that's going to be this side here. So 15 squared plus this side here, 9 squared, minus 2 times 15 times 9 times by cos a, remember, is opposite here. That's why I chose that as a, so cos 60. If I type that all into my calculator, then I'm just going to get that that will give me the magnitude of OB squared is going to be 171. After that then, I just want the magnitude of OB. So it's just going to be root 171, which to 3 significant figures is just going to be 13.1 kilometers. So let's just put that onto the diagram so I've got that bit of information there. So 13.1 there. So I've got all 3 sides now. So for part C, I need to figure out the bearing of B from O. So I need to figure out, let's use a different colour, B from O. So I start here at O, and I need to figure out how far I need to turn to get to B. So I know that this top part up to the line there is going to be 120, but I need to figure out what this part here is. So I've got my triangle. In fact, I'm just going to draw that triangle just over here, just outside of everything else. So the information I know about that triangle is that this side is 9, this side is 15, this side is 13.1. I want to know what this angle is, and I know that this angle is 60 degrees. So if I want to know a missing angle here, well, I could use either the sine rule or the cosine rule here. So I'd rather use the sine rule because it's a little bit easier. So you can see that we've got these two sides are opposite, or this side and angle are opposite each other, and so is this one here. Remember, it's the opposite angle to side that we're going to be using. So remember, it's going to be sine A over A, or A over sine A, it doesn't really matter which way you do it, equals sine B over B. So let's just put all of that information in. So we're looking for this here, so let's call that A at the moment. Okay, so let's call that angle A, let's call that angle B. This could be side B, and this can be side A here. So sine of A, we don't know what angle A is at the moment, but we know side A is 9, equals sine B, so sine 60, over 13.1. Then we just wanted the angle on its own, so I'm going to multiply both sides by 9. So that will now be 9 sine 60 over 13.1. Then I don't want sine of angle A, I just want A. So A is going to be equal to arc sine of 9 sine 60 over 13.1, which is just going to be equal to 36.6 degrees. Just remember though that that's not completely what we wanted, so I know that that angle there is 36.6 degrees. So in my diagram, this is 36.6 degrees. As we said though, we want all of this here, so my last step is just to do 120 plus 36.6 degrees, and my final answer for that bearing is going to be 156.6 degrees, so I can write that there. So for the last part for D, all I'm using is just the diagram that I had from before. It just wants the position vector of B relative to O. So actually all I want, if I just highlight this, is the position vector of this here. So this is going to be a bit harder than the last one, because actually in the last example, I already had 90-degree angles, which I don't have here. Okay, so I could do this in many different ways. So you might remember that we already worked out the position vector of A. You could also then work out the position vector of A to B, and then you could use that to figure out the position vector of B. But actually, probably the easiest way to do this is just to write down the little bit that we need there. So here I've got O. In fact, let's do that there. So here I've got O, and here I've got B. And I know that the length between the two of those is 13.1. Okay, so after that, let's just make that clearer, so 13.1. So after that, remember, if we want the vector, I need an I component and a j component there. So as you can see from my diagram here, I will need to split it up so that I've got this angle here. So I'm just looking back at this part here. So if this was going across there, so if I split that there, it's going to be 30 degrees and then the 36 degrees there, 36.6 degrees. So that's going to be 66.6 degrees. And then I need to figure out what this side is adjacent to the angle and what this side is opposite the angle. So to work out A there, that's the adjacent side. So I could say that cos of 66.6 is equal to the adjacent divided by the hypotenuse. So the adjacent is just 13.1 times by cos of 66.6 degrees, 66.6 degrees. And then similarly for O, well, I'm doing the same thing but with sine. So O is equal to 13.1 times by sine of 66.6 degrees. So I can work both of those out, and A is equal to, or approximately, 5.20, and then O is approximately 12.02. So to write that then as a vector, it would be 5.20, and then we're going down 12.02, so that would be minus 12.02. You could write that with IJ notation if you wanted to, so you could write that O to B is, you could write it like this, or you could write 5.20 I minus 12.02 J. Okay then, so now I think you should be fairly well prepared to do exercise 11F there. So have a go through that, and remember, just check your answers in the back of the book. If you have any problems, then please let me know. Thank you guys, and see you again on Thursday. Bye-bye.